Hi, algebra friends. Here we are looking at chapter 4. We're at the end of chapter 4 and we're in section 4.8. Here we're going to talk about writing equations from patterns. The suggested vocabulary here is looking for a pattern in inductive reasoning. Looking for a pattern seems more like a phrase that actually says exactly what it is. Looking for a pattern. So when you're looking at information and you're supposed to deduce if there's a pattern or not, it makes very good sense to look for a pattern. So actually looking for a pattern, as we have seen before, is basically one of the fundamental problem solving strategies that we have. So let's talk about looking for a pattern in terms of inductive reasoning. So inductive reasoning is when you look at a specific example and then you try to generalize what you think will happen. So when you're reasoning inductively, you're using a specific set of examples to reach like a generalized conclusion. I don't know, a really corny example would be as if you saw an arrow up, an arrow down, an arrow to the left, and an arrow to the right, and then I said, here's an arrow up. You would say, well, I've seen a couple of examples of what you're doing, lady, and it looks like this is a pattern. I'm going to go with the arrow is down. And these types of things, and then you can continue the pattern and say, okay, well, it looks like that's what we're doing. That's inductive reasoning. So you're looking at a couple of examples and you are speculating on what's happening. And that's what we do when we are looking for a pattern. We look at specific things that we have and then we kind of shoot and we say, okay, we think this is going to continue and this is how it may continue. So we'll start off our examples with example 1, and we have a very similar situation as we did with the little arrows before. We're going to study the pattern below. We're going to take a look at 1, 2, 3, 4, and 5 and look at the placement of the colored quarter or the colored part of the circle. And you see we've got up left, up right, down left, up left. And if you think that the next one will be up to the right, shaded up to the right, then that's kind of what I think would happen too. And so what you do when we look for a pattern is we just use the information previous to what we had. So if I see that we've got this here as that one, this is that one, then I'm going to be shading down to the right, and then the last one I will shade down to the left. Make sense, guys? I hope so. Not too bad, not too difficult. Let's take a look at, this gets a little bit interesting. Here now it says draw the 27th circle. Golly gee willikers, I don't want to draw 27 circles. Or okay, 27 minus 5 or minus 8, right? 27 minus 8 is going to give me 19 circles. I don't feel like drawing 19 circles. What I need to do is figure out a way to determine what's going to happen next. So what I notice here is that every 4, right? Every 4 seems to begin a new set. 1, 2, 3, 4, 1, 2, 3, 4, right? Every 4 begins a new set. I want you to think how you would figure that out. Pause me and kind of think about it. How would you figure out what to do about the 27th? Or what if I asked you something ridiculous like the 1027th? What would you do? Hopefully you're thinking about the fact that in 27, there's several groups of 4. So how many groups of 4 in 27? Well, we can figure that out by doing a little bit of long division. 4 goes into 27 6 times with a remainder of 3, right? So that means I've got 1, 2, 3, 4, 5, 6, right? 6 sets of 3 or 4 circles, right? Let me just do that. Okay, so here we go. 6 sets of 4 circles, right? And then I've got 3 more that are left over. And so those last 3 are the ones that I'm really concerned about, and that tells me how far in the pattern to go. So it tells me the 3 that are left over goes 1, 2, 3, and this guy represents the 27th. So the circle, let's make the nice circle. The circle that is the quarter is shaded in the lower right hand corner. All right, okay. All right, so looking at example 2, we're looking at patterns in a sequence. So here, instead of dealing with shapes, we're dealing with an actual sequence of numbers, and we talked about sequences in the last section. Here we are, we're going to find the next 3 terms in the sequence. So we have 3 to 6, 6 to 12, 12 to 24. Is this an arithmetic sequence? Hopefully you realize that there is no common difference, right? Because from here to here is 3, from here to here is 6, from here to here is 12. What you do notice is that there is definitely, this would actually be something called a geometric sequence because it looks like I'm multiplying by the same number each time. We'll get to that later. We talked about that briefly, a little bit mentioned. However, what I see is it looks like we are doubling the number before, right? So 3 plus 3 is 6. 6 plus 6 is 12. 12 plus 12 is 24. What are the next three numbers? Well, I'm using my inductive reasoning skills to say, well, I guess from 24, the next three numbers would be to double the one previous. So I would get 48, right? And then I get 96, and then I get 192. All right, so here's a nice fun problem. We're going to write an equation from data. The table below shows the average amount of gas that Rogelio's car uses depending on how many miles he drives. So Rogelio apparently, if he uses 1 gallon of gas, if he drives 28 miles, 2, 56 miles, 3, 84, and you can see the rest. So first we're going to graph the data. So as usual, I use the first, or what I call my independent variable. That's going to be my x, and along the y-axis I'm going to have miles driven, and I kind of tried to color code it a little bit so we can plot pretty easily. So if I graph this at 1 gallon of gas, he can go almost 30, about 28. So I'm going to put a dot right there underneath the 30. At 2, he can go 56, which is just below 60, a little bit below 60. 3, he can do 84, which is a little bit more below 90. And 4, 112, which is going to be around here. And 5, 140, which should be just about here. So you can see we've got this nice equation, and apparently if he has no gallons of gas, he cannot go anywhere. So I'm going to draw a line like this to represent what he can do. All right, so that's my graph. And now we're going to write an equation to describe this relationship. Well, I know x deals with the gallons of gas, and y deals with the number of miles driven. You should pause me and try to figure out how many miles he can drive. Like, what would this look like? So the number of miles that he drives is equal to what? How can I figure that out? Equal to what in reference to x? How can I figure that out? What would I do? Look at your graph. Look at your graph and look at the information that we have here in our chart. If you look, you see that for every 1 mile, every 1 gallon of gas, we can do 28 miles. Every 2 gallons of gas, 56. It looks like we have a straight up multiplication relationship. So y is equal to 28 times x. Okay, so here in this example, we're asked to write an equation with a constant. Now, I honestly think I'd put the numbers here along the axis. We're going to write an equation in function notation looking at the information, and they talk about using a constant. There's this idea that that our textbook writers have in their mind in reference to how they want you to write this equation. I'm going to tell you a slightly different way that I think might be a little bit more helpful. We've talked about lines, and this is obviously a linear equation. And we have a linear equation where y is equal to mx plus b. Some of you may have heard of it before. I don't know how much I've mentioned it to you. So this is a really helpful bit of information because y is just what it is. It's y, and x is what it is. Where m is this powerful concept called the slope, and b is this powerful concept called the y-intercept. We've discussed intercepts before. The intercept of a line is, we can have an x and y intercept, and it's where it hits the y-axis is the y-intercept, and where it hits the x-axis would be the x-intercept. This particular equation, y equals mx plus b, only talks about the y-intercept. So where is the y-intercept for our line here? It's at 3. So what I'm going to do is replace the b with the number 3. The next thing I'll do is look for the slope. The slope is how far up you go with respect to how far over you go. Sometimes slope, which is usually using m as a variable, is defined as the rise over the run, or the change. I'm going to use this triangle for change in y over the change in x. If we haven't done much of this, we will. So what I want you to see, if you just take one point, any 2 points really, these two, any 2 points, let's take these two because they're side by side. If I take these 2 points, how far up do I have to go? I go up a positive 2 direction and I go over in a positive 1 direction to get to the next point. Or if I choose these 2 points, I'll show you what I mean in a minute. It'll make sense, promise. If I chose, let's say, this point and this point, here I can go up how far? I go up 4 and I go over 2. But when I write that as a ratio or as a fraction, I would write either rise, the change in y is 2 over 1, or rise over run here, 4 over 2. Notice that both of these fractions give me the same value of 2. Your slope is 2. So what that tells me is that my m value can be replaced with the number 2. So my answer is 2x plus 3. Let's analyze how this affects this graph. So what this is saying is, if I put in an x value, when I do the work, I'm going to get the corresponding y value. I know I'm not done because I haven't done the function notation, but that's the easy part. Let's just check this concept real quick. So if I were to, let's say, put in the number 2 for x, right? Y is equal to 2 times, I'm placing 2 in for x, plus 3. 2 times 2 is 4, plus 3 gives me 7. So what this says is, when x is equal to 2, y has to equal 7. Well, let's see if that's true. Put 2 in, boom, I got it, 7. What this is confirming for me is that this equation really does describe this line, and I can try out different numbers and feel confident. So what the take home that I want you to get is that having the y-intercept and having the slope, when you have this form of a line, is super important because you can easily get the equation of the line. Let's finish off this problem the way the authors expected us to. They want us to write it in function notation, which we're not afraid of. Function notation is merely replacing y with f of the variable at hand, in this case x. So f of x is equal to 2x plus 3. And that's all we got. If this is not clear to you, which I suspect it might be a little bit troubling for a lot of us, don't feel bad. Let me know the next time we get together. Send me a text, an email, or whatever, and I can explain it a little bit better. I look forward to talking to you soon, and I can't wait to hang out with you. Take care, guys. Bye-bye.